Hello and welcome to this new video where I'm going to solve the remaining exercises of chapter 2. Exercise 11, we have to compute the improper integral from 0 to infinity of cosine x divided by x squared plus 1 squared. And we are given a hint to use the Cauchy's integral formula of order 1. So this is very similar to the one we solved in the previous video. So we can work on the same loop, which is the upper half circle with its diameter. And if you like, you can use the symmetric if you like, but then pay attention to the function you need to integrate. So we can take the same function actually here, eiz over z squared plus 1 squared. If you want to integrate over the lower half circle, you will have to take e minus iz. So we do as we did in the exercises that I gave you in class. So we start by writing the function to integrate, g, that we call g, as the ratio of a holomorphic function on a set which we'll have to determine now over z minus I squared. Okay? Now, if you want to integrate on the lower half circle, you'll have to change a little bit. You'll have to take eiz divided by z minus I squared divided by z plus I squared. Okay? But let us stick to the upper half circle. So once again we take, if you like, a convex domain omega, which is, so I will not draw a figure, it's the same figure as in the previous video. Same thing, just the denominator change. Instead of 1 I have 2. So I will have to use Cauchy's integral formula of order 1. Okay, so I have to differentiate. But same methodology work. So we have a loop in omega. Omega is convex and therefore simply connected, and therefore gamma r is homotopic to a point in omega, and f is holomorphic on omega. So I can apply Cauchy's integral of formula here, and I get 2 pi I times the index times f prime of I instead of f of I. There is dz missing here. And now it's very easy. So as before, the index is 1 because gamma is simple and positively oriented and has I inside. So we just have to compute the derivative. And if I didn't do any mistake, the result should be minus I e minus 1 over 2. Okay, just check that. And therefore, the integral happens to be, in this case also as well, pi over e. Okay. And we proceed then, so we use the same methodology. We split now the integral into 2 parts. The first part gives me the real integral that I need to compute, right? So same thing as before, just I have a square instead of a power 1. And I can do the same estimates for the integral over the upper half circle. So same thing, I use the triangle inequality, second form. So pay attention to the order. You cannot write 1 minus r2 because r is bigger than 1. So z squared plus 1, so in modulus, is bigger than this square minus 1. Modulus of the square minus 1. This is the second form of the triangle inequality. I cannot write plus 1 because it's wrong. Okay? So the denominator here is bigger than the denominator here, or equal. So when I do the inverse, I get something. Okay. So once again, the second integral by these estimates tends to 0, and therefore I conclude, and I get the same result as that we did in the last video. So same methodology works. And of course, you have the same remarks hold. You can use other variations on the same thing. You can integrate on the lower half. So, but just pay attention to orientation and the function. You have to change it. And once again, try to do for any power. Try to do for n what happens. Try to find a formula for a general n here. It should be doable, but it's more. Okay, it will take some time. Okay, so this concludes exercise number 11. Exercise number 12, also same idea. We have to find, the purpose is to find the value of this improper integral, 1 over xn plus 1, where n is an integer which is at least 2. Here we are, so we give you the path. Okay, I call it here CR. So we start actually by, so the methodology is we start by finding the singularities of the function, which are what? Which are the roots of Zn equal -1. And these roots, there's a formula for this loop, because we write -1 as EIP or EI 1 plus 2k pi, okay, because the exponential is 2 pi I periodic. And so we find n roots of -1, and these are given by z0, z1, z2, etc. And therefore I can write f of z, if f of z is the product of, so it's 1 over, so I can write 1 over zn plus 1 as 1 over zn plus 1 can be written as 1 over the product over z minus z0, okay, because there is a factor missing here, okay. So zn plus 1, but according to what you said, is the product. F is the inverse, okay. So I put 1 over the product except for z minus z0, and I divide by z minus z0. Okay. So same methodology, and we draw a picture. Here I took n equal 8, but you can take anything if you like. So, and of course here, so we continue in the same way. I will still present two options for writing properly Cauchy's integral formula. First way is a little bit tricky, because we could find a convex set omega containing z0 and not containing the remaining roots. So the biggest such possible path is this part between these two half lines. So this is what we call a cone. So omega is this region between the dotted line, the dashed line, and it contains, of course, the loop CR. It doesn't contain any of the remaining roots because these are at the boundary. And okay, so this is, it's not necessary to find an explicit formula for these lines, but it's enough to draw a picture like this. So now I understand that you are working in this cone, which contains the loop, and omega and f is holomorphic in this cone, because the other singularities are at the boundary. So, and of course, if you like, you can take a smaller one, not containing at the boundary. Okay, but this is the idea. So here, what do we have? We have, so omega is convex and therefore simply connected, and therefore CR is homotopic to a point, and F is holomorphic on omega, and CR is, yeah, that's it. So, and therefore we can apply Cauchy's integral formula of order 0. Okay. And here, of course, the index is 1. Just have to say why, for the same reason as before. So this is the first way. The second way is to take omega to be C without the remaining roots. And in this case, F is holomorphic on omega. And we can check that the straight line homotopy, right, happens far from the remaining roots, the remaining singularities. Okay, so the straight line homotopy doesn't touch Z1, Z2, Z1 minus 1. And here's the picture. So the straight line homotopy happens actually inside the loop. Okay, so we don't touch. Okay, I hope this convinced you that I can shrink or collapse my loop to a point in omega. Okay, because we are far from the remaining roots. And so we can apply Cauchy's integral formula, and we get the same result. So you have two ways for justifying the use of Cauchy's integral formula, and usually I put 3 points or 4 points on this because we have to be rigorous. Okay, so it's completely the same. Now the computation of f of z0 is a little bit tricky. Here it is. F of z0, because f is continuous at z0, is the limit of f of z. But f of z, if you go back to the definition, is actually what? Can be written as z minus z0 over zn minus z0 to the n. Right? Because it's zn plus 1, so I can factor by it. Okay? And now this is what? This is Newton's ratio. So the limit of this ratio is 1 over the derivative of zn at the point z0. The derivative of z to the n is nzn minus 1. So I just have, so this gives me 1 over nz0 to the n minus 1. If I multiply by z0, why do I do this? Because z0 to the n is minus 1. So it's minus z0 over n, and it gives you this result. Minus 1 over n times ei pi over n. This is a little trick that you may learn, because otherwise it would be a little bit difficult to, if you write it the other way, it would be 1 over z0 minus z1, z0 minus z2, etc. And this is hard to compute directly. Okay, so use this trick. And now we are done actually, because now we can compute, just replace f of z0 by its value, and we get this result. And in the next step, we split our integral into 3 parts, because we have now 3 concatenation of paths. The first path gives me the integral I'm searching for. The second one would tend to 0, as we shall see. And the third one actually is the integral over the third part of the loop. So, yeah. And I did a parameterization, because a parameterization here is just ei 2 pi over nt, t from r to 0, because we are in the, so pay attention to the orientation. Okay, this is my path. So this is the first integral. Second integral should tend to 0, and this is the integral over the third path. So here it's r ei 2 pi over n, 2 pi I over n. Okay, so, and we did something similar before. Okay, so we have 3 parts now, and this is the derivative. Okay, now this third integral actually is related to the first one. Okay, because the ei 2 pi over n to the power n is just 1. Okay, and this is minus the integral from 0 to r, so I have just this ei 2 pi over n in factor. So the integral that I already computed is this constant times my integral, which I'm searching for as r tends to infinity, plus this that I will prove now in a moment that tends to 0. Okay, so this is the strategy. And why this tends to 0? By the fundamental estimate. So I use the triangle, second form of the triangle inequality. It's modulus of z to the n minus 1, so rn minus 1, and the length of gamma r is 2 pi r over n, because it's just a sector. Okay, this is okay because it's not the whole circle. It's this. It's 1 over n of the circle. So anyway, this tends to 0, and therefore, in the equation, so I have this equation. I let r tend to infinity, and I get this relation. And now, just a little algebra. Call this in, and just rewrite. So just divide this number by this number, and rearrange. So we can factor by ei pi over n in the numerator and in the denominator. So then I cancel. So I get minus 2 pi I over n over e minus I pi over n minus ei pi over n. And this would give me minus 2i sine by Euler's formula. Then I simplify, and I get finally a very simple result, pi over n over sine pi over n. And the result should be real, because it's a real integral. Okay? And this is a remarkable formula. Okay? It's not easy to compute this integral. It's possible. There are other methods to compute this integral, but they are more, they are lengthy actually. Okay, maybe you can integrate by parts. I don't think if the integration by parts would, even for the case t n equal 4 or n equal 3, is very tedious because you have to factor this and decompose into simple fractions and so on. So it's very complicated actually. Okay. So in particular, when you take n equal 4, you get pi over 4 over radical 1 over radical 2. Okay. So yeah. So even for the case n equal 3 or n equal, for n equal 2, it's just the arctangent, so just pi over 2, right? For n equal 2. For n equal 1, it's divergent, so it doesn't exist. So I need at least n equal 2. For n equal 3, I get pi over 3 over sine pi over 3, and so on. Okay? Yeah, so this concludes exercise 12. I hope so. This is a classical strategy. Okay? Let me go back over it one more time, just to. Okay, so I hope it's clear. Not trivial. Okay, so I will not ask you such questions in the exam. Or maybe if I want to ask you something, I will take a particular case like t cubed plus 1 or t4 plus 1. Next exercise. Definition. A branch of the logarithm or determination of a logarithm on an open subset of C star is a continuous function whose exponential is z. So it's, if you like, it's the inverse of the exponential. It's a continuous, so this is why we call it a logarithm, because it's the inverse of the exponential. Okay, but the exponential is not injective. So actually, this is why there are many branches of the logarithm. And we have to work on C star because len of 0 is not defined. Okay, omega 0 should not be in omega because the exponential never vanishes. So if 0 was an omega, I should have EH0 equals 0, but the exponential never vanishes. Okay, so I must work on an open subset of C star. Now, there is no branch of the logarithm on C star. I will not get into the details here, but there are branches of the logarithm if we remove half a line from C star, from C. Okay, and what you call the principal branch or the principal determination is obtained when you take omega equals C without the negative real axis. This is what you call the principal branch of the logarithm. It solves this equation. Okay, and now the question is, if omega is simply connected, show that there exists a branch of the logarithm. And more generally, if we have a holomorphic function that does not vanish, then I can find a holomorphic function whose exponential is the given function. Okay, so this is a particular case of this just by taking f of z equals z. Okay, let us start with the particular case. Since 0 is not in omega, 1 over z is holomorphic on omega. And since omega is simply connected, I know that 1 over z has an antiderivative. Why 1 over z? Because you know we should expect that the derivative of the logarithm should be 1 over z, as you know. So this is why I consider 1 over z. Okay? So if you call capital F such antiderivative, consider the function e to the f z over z and compute its derivative. So if you apply the ratio rule, you'll get z squared in the denominator, z times the derivative of e f z minus the derivative of z, which is 1 times e f z. Okay? And now the numerator is 0. As you may check. If the g prime is 0, okay, why the numerator is 0? Because if we simplify by e f z, I get z f prime minus 1. But since capital F is an antiderivative of 1 over z, then f prime is 1 over z. So z f prime is 1. So the numerator is 0. Okay. So we have a holomorphic function whose derivative is 0. But since omega is simply connected, it's in particular connected by definition. So G is a constant. Therefore, EFZ over Z is this constant. Now, since the exponential never vanishes, then K is different from 0. If K is different from 0, then I can solve the equation e to the Z equal K, and I find one element A. So, as you know, the exponential is surjective from C into C star. So any non-zero number is the exponential of something, as you know from the first course. And that's it, we are done. Now, so I write EFZ equal KZ, so it's EA times Z. When I divide by EA, I get this. So now the function I'm seeking is just capital F of Z minus A. So otherwise stated, what is the branch of the logarithm here? Is actually, it's an antiderivative of 1 over Z, but there is a constant to adjust things, okay? Because here, when I say one antiderivative, okay, I'm not specifying. There are infinitely many antiderivatives that differ by a constant. Okay, and this antiderivative, if you like, what happens if you take z equal 1, for example? Suppose 1 is in the domain, then we should get f of 1 minus a equals 0. So f of 1 equals 0. Right? Okay, and now this same argument here can work more generally in the following context. So yeah, so that's it. So I found one branch of the logarithm. More generally, instead of taking 1 over z, I take f prime over f. Okay, f prime over f is holomorphic on omega because omega has no 0, right? And since omega is simply connected, there is an antiderivative capital F. And now I take g of z to be e to the fz, capital Fz over small fz. So same thing, just instead of z, take small f of z. And we can compute the derivative and find 0, right? Because f prime is capital F prime is small f prime over f. So the numerator vanishes. Okay. So by the way, this is f prime should be not inside the exponentials, outside. And this is f of z squared. It's the same reasoning actually. And I repeat the same thing. So this is actually also there is an error here because this is just k. There is no f of z here. Sorry for the errors. There's no f of z here. Okay. So once again, I take k to be the exponential of some complex number, and then I find, so capital F of z minus this a will be, if you like, so the exponential of this would be small f of z. Okay, last exercise. We have a simply connected subset of C, and we have a harmonic function of a real variable. So I consider here actually u as a function of two real variables. Here I identify omega with a subset of R2. I need to show that u, which is a function of two variables, is the real part of a holomorphic function. Because this is the kind of converse to a previous exercise. We know that the real part of a holomorphic function is harmonic. Now we are trying to prove the converse, but under the extra assumption that the domain is simply connected. Because if the domain is simply connected, you can give counterexamples. Okay? And you are given a hint. So consider del u over del x minus I del u over del y. Okay. Let us show that G is holomorphic. How do I know that G is holomorphic? I just need to check that G satisfies the Cauchy-Riemann equation. Okay? So the derivative of the real part is actually the second derivative with respect to x, and the derivative of the imaginary part is minus, right? Now, since u is harmonic by assumption, these two are equal because they sum to 0. So Therefore, I have the first equation of Cauchy-Riemann, right, for the real part. For the imaginary part, is the same thing. Okay. Therefore, we have a function, a complex function of two real variables whose real and imaginary part are harmonic, are holomorphic. Therefore, G is holomorphic. Okay. This is the first thing. So G is holomorphic. Now, since omega is simply connected, any holomorphic function has an antiderivative. So let capital G be an antiderivative of small g. And take f to be the real part of capital G. Then, by chapter 1, I know that capital G prime is the derivative of f with respect to x minus I times the derivative of f with respect to y. This is by chapter 1. Okay. And now, the derivative of f with respect to x is the same. So it follows that the derivative of f with respect to x is the derivative of u with respect to xy, because what is u here? If you go back. Okay, so capital G prime is small g, and the real part is del u over del x. So therefore, and the imaginary part is that. So if I identify the two, okay, so because G prime is small g, so this is small g. So small g is del u over del x minus I del u over del y. So by identification, I get these two equations. Okay. So here I consider u and f as a complex variables of two real numbers, two real variables. So what do I have here? I have the gradient of f is the gradient of u. And since omega is connected, f and u differ by a constant. And that's it. So u is the real part of g plus c. And that's it. We know that g is holomorphic. Therefore, we started with the harmonic function u, and we proved that u is the real part of a holomorphic function with g plus c. That's it. So, yeah. So this concludes exercise 14 and concludes this video. In the next video, I'm going to cover section 3.1 of chapter. So thank you for your attention.